Imagine the terrifying sight of a massive space rock plunging toward Earth. Such scenarios often raise critical questions. Can humanity prevent a catastrophic event of this magnitude, or are we powerless in the face of celestial impacts? These pressing concerns have driven NASA to undertake unprecedented measures, such as flying a spacecraft directly into an asteroid's path. The results, however, defied expectations and revealed surprising new challenges. What unexpected developments occurred, and what are the implications for our planetary safety? Join us as we delve into the intriguing mystery of a space rock impact that has left NASA experts both astonished and searching for answers. The DART mission. Testing planetary defense. For decades, engineers and scientists have worked tirelessly to develop strategies to protect Earth from asteroid impacts. One of the most significant efforts in this area is NASA's Double Asteroid Redirection Test, DART. This mission was specifically designed to test a new planetary defense technique by intentionally colliding a spacecraft with an asteroid to alter its trajectory. The target for this ambitious mission was a pair of near-Earth objects, Didymos and its moonlet Dimorphos. The term Didymos, meaning twin in Greek, reflects the binary nature of these celestial bodies. Discovered in April 1996 by scientist Joseph Montany using the Spacewatch telescope at Kitt Peak National Observatory in Arizona, Didymos later revealed a small moon orbiting it. This discovery was confirmed through radar imaging from NASA's Goldstone Solar System radar in California and Puerto Rico's Arecibo Observatory. Though these asteroids posed no immediate threat to Earth, they were ideal candidates for the DART mission. The goal was to assess whether a spacecraft could slightly alter an asteroid's orbit, proving a potential method of planetary defense. The science of deflecting asteroids. The fundamental idea behind the DART mission was straightforward yet revolutionary. Redirect an asteroid by colliding a spacecraft into it at high speed. The objective was not to destroy the asteroid but to nudge it into a safer orbit, minimizing the risk of a future collision with Earth. Hollywood depictions often showcase dramatic asteroid destruction, such as planting explosives to obliterate the threat. However, this approach has significant drawbacks. Blowing up an asteroid could create multiple fragments, each with unpredictable trajectories, potentially increasing the risk to Earth. Instead, scientists advocate for more measured solutions like deflection or gravitational towing, where a small force applied over time can alter an asteroid's path without creating debris. The precision required for such missions is immense. A miscalculation in the force applied could leave the asteroid's trajectory unchanged, or worse, direct it closer to Earth. Hence, testing these methods on a distant asteroid like Didymos was crucial to understanding their feasibility and refining the techniques. The potential danger of asteroid impacts. While the DART mission was a milestone in planetary defense, the grim reality of asteroid impacts remains sobering. A collision with a large space rock could have devastating consequences. The immediate destruction at the impact site would be catastrophic, and the aftermath could unleash global chain reactions, including tsunamis, firestorms, and atmospheric changes. For example, consider a space rock roughly a mile wide traveling at 30,000 miles per hour. The energy released upon impact would be equivalent to a 1 million megaton bomb, far surpassing any man-made explosion. Even smaller asteroids can cause significant damage. A 200-foot wide asteroid could deliver energy comparable to the most powerful nuclear bomb, flattening structures within a 5-mile radius. History provides chilling examples of such events. On June 30, 1908, a 40-meter wide asteroid exploded over Siberia's Tunguska region, devastating a forested area the size of London. This incident remains one of the most destructive asteroid impacts in modern history, emphasizing the urgent need for effective planetary defense systems. The global threat and efforts to mitigate risks. Asteroids pose a unique challenge due to their unpredictable nature. They can suddenly appear or change orbits due to cosmic events, leaving little warning before potential impacts. In the worst-case scenario, humanity might have only weeks or months to prepare for a disaster. Recognizing this threat, international collaborations have emerged to monitor and address asteroid risks. June 30th, the anniversary of the Tunguska event, is now celebrated as International Asteroid Day. This initiative raises awareness about the dangers of near-Earth objects and promotes research into planetary defense strategies. The United Nations and space agencies worldwide are actively developing comprehensive programs to improve detection and mitigation capabilities. Advanced telescopes and radar systems constantly monitor known asteroids, while missions like DART provide valuable insights into deflection techniques. The road ahead. Preparing for the unknown. Despite significant progress, defending Earth from asteroid impacts remains a complex and evolving challenge. The vastness of space and the sheer number of celestial objects mean that unknown threats could emerge at any time. Continuous research, international cooperation, and technological advancements are essential to improving our chances of averting disaster. The DART mission was a bold step toward a safer future, but it also highlighted the unpredictability of space and the need for vigilance. As we continue to explore and understand the cosmos, safeguarding our planet from celestial threats will remain one of humanity's most critical endeavors. Around the clock, NASA and other agencies monitor space rocks and comets near Earth, analyzing any slight change in their orbits. In emergencies, NASA issues space rock warnings. Over the past 2 decades, 3 such alerts have been issued, with Earth narrowly avoiding disaster each time as massive celestial objects missed the planet by thousands of kilometers. However, relying on chance is not a sustainable long-term strategy. Experts worldwide agree that asteroid deflection involves 2 primary methods, either forcefully altering the asteroid's orbit or towing it away. NASA's DART, Double Asteroid Redirection Test mission, launched in 2021, embodied the first approach. Its goal was to crash a spacecraft into Dimorphos, a near-Earth object (NEO), to test a groundbreaking planetary defense strategy. If successful, the collision would permanently alter Dimorphos' orbit, slowing it slightly. Even small adjustments to an asteroid's orbit can have significant long-term effects, potentially allowing us to divert a threat years in advance. While Dimorphos posed no danger to humanity, the mission served as a proof of concept for redirecting potential threats away from Earth. The DART mission. A collaborative effort. The DART mission was a joint endeavor involving NASA's Johns Hopkins Applied Physics Laboratory and international partners, including agencies from Italy, Japan, and the European Space Agency, ESA. Dimorphos is part of a binary asteroid system, orbiting a larger asteroid named Didymos. The smaller Dimorphos, a moon-like rocky body, completes an orbit around Didymos every 11.9 hours at a distance of about 1 kilometer. The entire system orbits the Sun every 2.1 Earth years. In October 2022, Dimorphos made its closest approach to Earth since 2003, passing about 10.6 million kilometers away. An ideal opportunity for the DART mission. The spacecraft itself was relatively simple compared to other space probes. About the size of a refrigerator and weighing 610 kilograms, it was equipped with a high-resolution camera called Draco, Didymos reconnaissance and asteroid camera for optical navigation, along with autonomous navigation systems. It also carried a small companion spacecraft, ICIA Cube, developed by the Italian Space Agency, ASI. SE Cube was designed to document the impact event with its 2 cameras, Luke and Leia. Launch and journey to impact. DART launched on November 23, 2021, aboard a SpaceX Falcon 9 rocket. The spacecraft traveled through space for 10 months before its impact. In the final approach, when DART was 990,000 kilometers away, its navigation system took over. The spacecraft closed in on Dimorphos at an astonishing speed of 22,000 kilometers per hour. Just 24,000 kilometers from its target, Dimorphos appeared on Draco's camera as a single pixel. As DART neared, it transmitted images showing Dimorphos as a loose collection of debris, a remnant from the solar system's early formation. Seconds before impact, DART captured its final image from just 12 kilometers away, with each pixel representing roughly 3 centimeters. This last transmission abruptly stopped as DART intentionally collided with Dimorphos, ending its 17.5 million kilometer journey. The dramatic final image remains a favorite, encapsulating the mission's thrilling culmination. The impact and its results. The collision was a resounding success. NASA initially expected Dimorpho's orbital period to shorten by at least 73 seconds. Instead, the impact reduced its orbit by 32 minutes, from 11 hours and 55 minutes to 11 hours and 23 minutes, a change more than 25 times greater than anticipated. This outcome was verified through observations from Earth-based telescopes, including the Southern Astrophysical Research Telescope in Chile. Additionally, telescopes captured striking images of a 10,000-kilometer debris trail resembling a comet's tail 2 days after the impact. The explanation for the significant orbital change lies in physics. The collision transferred momentum to Dimorphos, bringing it closer to Didymos and accelerating its orbit. The impact released energy equivalent to 19 gigajoules, or about 5 tons of TNT, creating a crater up to 150 meters wide on Dimorphos' surface, remarkable given that the asteroid itself is only about 160 meters in diameter. Post-impact observations and insights. A-Cube, which separated from DART 2 weeks before impact, captured detailed images of the collision site just minutes after the crash. Its photographs showed massive plumes of debris radiating from Dimorphos, some swirling like planetary rings. The debris pattern suggested a mix of fine dust and coarser material, consistent with impact simulations. Earth-based and space telescopes, including the Hubble Space Telescope and the James Webb Space Telescope, continued to monitor the aftermath. Hubble captured images of expanding plumes and curved debris trails, while Webb provided dramatic infrared views of spiraling material. The path ahead, Hera mission. Further analysis will be conducted with ESA's Hera mission, set to launch in October 2024. Hera will examine the impact site in greater detail, deploying nanosatellites to study Dimorphos' internal structure and measure the energy transfer from the collision. This mission aims to build on DART's findings and enhance our understanding of asteroid deflection techniques. A milestone in planetary defense. The success of the DART mission marks a significant milestone in planetary defense. It demonstrates that humanity can alter the trajectory of potentially hazardous asteroids, paving the way for future strategies to protect Earth. The mission underscores the importance of global collaboration in addressing cosmic threats, showcasing what can be achieved when nations work together to safeguard our planet.